are you ready? Okay, I would like to. Okay, good evening, everybody. Before the talk, I would like to give a brief introduction to Dr. Britton Chance. Britton Chance is amazing. He has won prizes ranging from the Olympic gold medal to National Medal of Science. He obtained 2 PhDs, one in physical chemistry from the University of Pennsylvania in 1940, and the other in biology physiology from Cambridge University in 1943. Among his honors are a member of National Academy of Sciences, foreign members of Royal Swedish Academy of Sciences, foreign member of Royal Society, member of Royal Academy of Arts and Sciences. Since his first U.S. patent award at age 17, he published more than 4,000 papers and books. Britton has employed a rare combination of brilliance, drive, and good fortune to become the most prolific scientist of the 20th century. Between 1941 to 1945, Britton joined world effort focusing on radar in MIT. He developed a device providing critical radio information for anti-aircraft gun-pointing system. He was named group leader of the precision circuits section of the receiver components group in 1943, and was elected to the steering committee chaired by Lee Doveridge and Robbie. By 1945, he was supervising 300 people as associate director of Lee Howell Division of MIT Radiation Lab. I know today we may have many students from the electronics. Britton was appointed to the President's Scientific Advisory Committee in 1949 to 1960. After the war, Britton resumed work in the enzyme substrate problem in Stokes former. Using the stop flow apparatus, he and Howell Theria identified and treated a coenzyme for the first time. They found that the enzyme substrate reaction did not proceed without the binding of the coenzyme. The process is now identified as the Britton Chance mechanism. Britton and his colleagues demonstrated the first 4-organ magnetic resonance spectrum in the late 1970s. Shortly thereafter, in early 1980s, Britton and his colleagues first demonstrated MRAs in human subjects. The success of optical spectroscopy for probing intact organelles stimulated Britton to push the optical method toward the living tissue. The rapid progress of the in vivo MRAs foreshadowed current development in optical spectroscopy and imaging of deep tissue. Britton has been a central figure in the development of a new field. He is regarded the father of biomedical photonics. Britton Chance is one of the giants of biochemistry and biophysics. His research draws from many disciplines, particularly electronics, clinical medicine, biology, and physics. Also, Britton won a gold medal in sailing in 1942 Olympics. This is a short version to Britton. Now that's very common.
Thank you, Ching Ming. I come to you as a student. I welcome you as students. I'm still a student. The thing I like most is learning something new and doing something new. I'm different from Aaron. I used to be a biochemist, but now I'm biophysicist, bioelectronics, and all the new things, including metabolomics. So I want to welcome you to the new field, I want to tell you how important it is to me to get a message to you students, to be diligent, to know that you'll be learning the rest of your lives. So don't stop now. Well, my story begins with, at age 13, I played with optical devices and found that the magnetic compass in my father's yacht was hard to follow with a heavy steering wheel. And I got tired. So I decided that a servo mechanism, a robot, would be a good thing. And playing around with light sources and photocells, as you can see here, if I can find the pointer somewhere, we were able to project a light beam onto a mirror, and then that mirror would swing or stay stationary as the ship swung. And with photocells, which were very leaky in those days, that was 1934, cesium, antimony, and silver, and we were able to track the motion of a vessel and to control it with its rudder. Well, that was fine. In fact, as the previous slide shows, I was introduced to enormous tankers which went from Philadelphia to Galveston, Texas and back, and left out Mr. Bush, fortunately. And so this gave me experience with big ships. Well, it wasn't long before the British GE picked up on this, and I was sent to London aboard a refrigerator ship that brought beef from New Zealand and Australia to the British palate. You know, British beef is a great thing, but it wasn't British beef at all. It was Australian beef. And so that did one great thing for me. It got me a fellowship to Cambridge University. And there, before the ship sailed, I went and met the son of R.A. Millikan, the oil drop Millikan, the data doctored Millikan. And his son was not really agreeing with the father. He was a wonderful fellow, about so high, terribly energetic, with a very long nose. And we hit it off right away because the test of qualifying for the research studentship in physiology laboratory was to be able to climb around a coil, a column in the court where Newton lived and did his work without touching the column. So I passed and entered the physiology laboratory. Now, physiology then was what we call blood and guts physiology. It was surgery, anatomy, and so forth. And Sir Joseph Barcroft, who you may not know of, was really a famous physiologist, and he would actually demonstrate on a sheep every Tuesday night. So every Tuesday night you went to the amphitheater in physiology, and he demonstrated. Well, that got me out of physical chemistry into physiology, which is a good thing. I've never regretted it. But soon I was on my way to Australia and back, and as I got back, the clouds of war were growing over Europe, and while Chamberlain said, "Peace in our time," it was a four-letter word. And soon after, Hitler marched into Czechoslovakia, and all the non-Brits, including Max Perutz, were either interned, as was Max, or took a ship back to their native country. And as you know, Max lost 4 of these very good years trying to make icebergs on which the planes could land. But Max will tell you about that himself. So back in Philadelphia, Glenn Milliken and I arrived in a laboratory of physiology. Well, of course, we were physiologists. And that was the laboratory of Dr. D.W. Braun, who was a well-known physiologist. And indeed, we were able to follow my dream, and that is to prove the Michaelis-Menten theory of enzyme action. That theory predicted that the enzyme would collide with the substrate and make a compound and then break away, just in the manner you were talking about, Aaron. And the compound had never been isolated. It was all hypothesis and based. So the enzyme, which was suspect of being useful, was called peroxidase. Well, you eat horseradish very much here, and that's very tasty. But it has an enzyme called peroxidase, which changes its color when it combines with the substrate. And that brought us back into optronics, because we had to make a spectrophotometer. Not an ordinary one, but one was working in the millisecond region, which had never been done before. And so we looked for the combination of enzyme and substrate to give us a color change. And indeed, we had to invent an apparatus because the reactions were occurring in the millisecond region. And you know when you try to mix water and milk that you don't get it done in a millisecond. So we had special mixing jets, which I drilled out with a dentist drill and stuck onto this device at the proper place right here, a small 1 millimeter tube. Well, that introduced me to hydraulics, because the Prandtl-Kármán theory of laminar and turbulent flow was necessary to examine here to make sure that there was turbulent flow. Everything was rapidly mixing. And indeed, we did that. And this has been the method which is now the protein folding people love, but they don't remember, but that's all right. In order to solve the differential equations for E plus S, these are nonlinear differential equations, as I shall show you. There they are, one for the substrate disappearance and one for the intermediate formation. And these circles are experimental data obtained with a photoelectric method. But to solve those equations, we needed a digital computer. That didn't exist, but we did have a mechanical differential analyzer, which had just been completed at the Electrical Engineering School of the University of Pennsylvania. There was no air conditioning, and it made a little bit of heat. But we worked through the summer, and the nice thing about the mechanical analyzer is that each shaft is a variable. So you know whether the substrate is disappearing because that goes fast, and whether the intermediate is forming. And so it was vivid. Furthermore, when you change a constant in your laptop, you do it with your fingers. We did it with a screwdriver and a gear. And you put one gear on, and you put the other gear on. We knew what we were doing. You don't know what the hell you're doing. So this was the first use of a computer in biological science, and a very good start for me. So we did prove the Michaelis-Menten theory, and believe it or not, the Journal of Biological Chemistry accepted the paper immediately. But they changed all my molar to moles, not understanding the difference between the two. Well, and these were the results. And I said, this stock flow has lived on till today because it's the most convenient way. And of course, if you want to talk tech transfer, it's made by several companies now. But the main thing was, which introduced the computer to biochemistry and biophysics. And because I had won my spurs in computer technology and electronics, I was tapped, I guess, on the shoulder to come to MIT in the summer of 1941 when the clouds of war were gathering. And I was introduced to some famous physicists, Dubridge, Purcell, Robbie, so forth, with not a word as what they were doing, but whether I was a good guy or not. Well, I turned out to be a good guy, and the next thing I knew, I never got back to Philadelphia. I was pinned a badge on me and sat to work on a workbench with an apparatus that wouldn't work. This was called a radar timing device. At that time, we used vacuum tubes, no transistors, but we also had circuits that drifted, weren't stable, and so my job was to stabilize. My companion there, if you probably don't know, was Al Grass, who made Grass Instruments and made Grass Fellowship. And we hit it off perfectly, and so with knowing which end of the soldering iron to grab, I could get to work immediately to make a range-finding system. Remember, radar sends out a pulse, and then sometime later it comes back. That's in the microsecond time range, and that was short time for us. And we had to make a device accurate to 1 part in 30,000 because the military mind didn't want to miss the target. I didn't care. Well, I really did, but anyhow. And I was plumped into the steering committee of the radiation laboratory, and you can see I Robbie with his pipe, Bonner, Pollard, so forth, Lee Dubridge, the president of Caltech, and here, and Zacharias from MIT. Well, I was just a kid. I was the youngest member of the steering committee, and why they tolerated me was only because I was just out of diapers. So, but it was a good group. I've never been with it. Yvonne Getting invented GPS, which you all know about, and all went on to famous careers. So each one had a division of maybe 400 or 500 people set on different radar projects. And you talk about tech transfer. Don't worry about it. We had GE, Westinghouse, Motorola, Philco bowing to us. They don't do it now. We told them where to go. And of course, GE came in the GE suit. You could recognize them at 50 yards. And Westinghouse and GE were competing. And of course, Philco and Motorola did it much better, including, this was Bell Labs. The entire Bell Labs was set to work on this. And there was a conflict of interest. M.J. Kelly, who was chairman of the board of AT&T, would thump the table and say, I've got to think of my stockholders. I would say, go to double toothpicks. And so we really had our tech transfer in an ideal thing. And I think there was probably about $500 million worth of equipment made in the first year. And that continued. And one of the main things was anti-aircraft control, because the Brits were having trouble with the fleets of German bombers which came over in the night. Well, now the CHL system, which Watson Watt set up, and indeed he purloined me when I was in England to find out what I was doing. I asked him what he was doing. He said, "Oh, radio direction finding." Oh, all right. Well, but he was very active, and of course, it wasn't long before I was sent over in 1943, as St. Paul's Church was crumbling in ruins, to trade secrets with the Brits, because they had their own radar development, but we had the advantage of productivity and could make these sets very rapidly and effectively. And as I went to the relocated laboratories, they had been taken out of any nearby bombing site, to schoolhouses in Malvern, England, and there, believe it or not, I met all my colleagues from the physiology laboratory. Alan Hodgkin and Richard Keynes and Andrew Huxley had been my roommates next door, all working on radar, different places. Well, there I met Freddie Williams, who was really a circuit genius, and also Moody, and we turned out to have a very close coupling. Now, this particular device tracked an airplane at 6 miles distant and 30,000 feet altitude with an accuracy of 1 degree in angle and 1 yard in range, and enabled a Bell Labs computer, which is good, which had potentiometers that big in it. It was an analog computer, which controlled a 5-inch hydraulically controlled gun. And that was a lethal weapon. It shot down 99% of the buzz bombs, defended the beach at Anzio and Normandy, so the German planes just didn't get anywhere, or if they did, they got shot down. So it was a success, but I can tell you there were nervous moments because we had to demonstrate to the military. Well, what the radar lab did was much more than just make the radar, which you see at all the airports, because the airport radar is going around continuously, as you see. But the technical problem was we had to identify and track each airplane and label them so that they could have a big screen with the ID of the airplane, the position of the airplane, when it was going to land, and so forth. And that you can see, and it's rather satisfying to see radar at all the airports and in the nose of every airplane. There isn't an airplane that doesn't have radar. And so there were peacetime things. Then you will see an airplane sometimes, which we call a busted duck, but that won't mean anything to you. It was very pregnant because it had a big gray dome underneath it. And that is AWACS, early warning, which flies with an enormous radar on top of the airplane and gives an extended range because it's flying at 30,000 feet and therefore can see around the curvature of the Earth. So that was a bit useful. This I've already mentioned. I mentioned Ivan Getting, and we started this one. Long-range navigation was a pulse system. But the more interesting development, in order to transport data from AWACS down to the ground, we had to have a data transmission system. And you invented pulse code modulation. Well, I'm so glad that we made something for Mr. Hewlett and Mr. Packard to earn millions of dollars with. So that was PCM. And that was also, we made the first integrated circuits. We didn't have transistors. Mr. Shockley had done his thing, but we did have very small vacuum tubes, and they were little packages. So this was a chapter of intense activity of building computers that would fly and that would not only predict when to drop the bomb, but they would allow you to navigate. They would give you your latitude and longitude. And this won a competition for the best airborne computer over Bell Labs, Norton, Sperry, the big names of the time. And guess who in Bell Labs were supposed to do it? Well, Charlie Towns of laser fame and Dean Wooldridge of Wooldridge-Raymo. Guess what they did? Nothing. On the other hand, maybe it's better that Charlie Towns competed to invent the maser and the laser. So this little episode is interesting because nothing was published from 1938 onwards in technical language. The government just put a clamp on it. So when Mr. Press Eckert got a contract to recalculate the ballistic tables from Aberdeen, he had no technology. And I knew this, and I knew Press, and I said, Press, I'm going to give you a contract to develop something for me. I know damn well you won't do it, but we can therefore give you access to all our secret information. And believe it or not, it was Bruno Rossi's counting circuit that got built into the ENIAC. Of course, Press didn't like to talk about this, but the truth comes out eventually. So the thing that it did give us, it gave us graveyard shift access to any computer that they built at the time. And of course, you know, when the graveyard is from midnight till 4 a.m. So that we found it very useful and could continue our work on differential equations. Well, when I was in Sweden, I was a bit seduced by the Olympic ideal because the Scandinavians, you know, Pavel Nurmi and all those people, Finland, Sweden, Denmark, Norway, are very Olympic-minded. In 1952, when the Olympics were scheduled for Helsinki, as sort of reparation, remember, the Finns had to fight both the Germans and the Russians, and they were very strong people, and I was told that by my friends in Sweden, let us build you a boat so that you can compete in the Olympics. Well, that meant I had to spend a month training dawn till dusk. Now remember, dusk doesn't occur till midnight in Sweden in the spring. So we trained like hell and sailed over from Stockholm to Helsinki, avoiding the Russian trap on the way. The Russians had a certain area which if you entered, you got a 2 weeks vacation for free. I had made it to Helsingfors and found that the first races didn't go well. We were despondent, and then we got ourselves reorganized and the boat going fast. And in the last race, we had to come first. Norway had to come fifth. Well, that's what happened. So we got the gold, and they got the silver. The Norwegian team had a woman in it, and this is the Swedish team, and this is myself and my cousins, 2 twins. So it was an experience that I never wanted to do again. The tension was very, very significant, especially since we had to win the last race. But we did. And so that's been memorable. And I did at that point decide to train the USA in the Olympics, and I was happy to say that subsequently we got a gold and a bronze. So the Russians invited me to the first international race in 1963 in this kind of boat, and we sailed from Helsinki to Tallinn, where, believe it or not, the Russian fleet was anchored. And of course I wasn't supposed to know that was where they were. And we didn't know exactly where to go. But there is an etiquette you have in yachting. It's international. When you pass another ship and you pull down your flag halfway, they have to respond. Well, that was like a fox among the chickens, because they didn't expect to see these guys running after, hauling their flag. At least was a bit of a reparation. Well, we finally got there and took the cup, The cup was an enormous cup so high with pictures around the top of the Dnieper Dam, Red Square, you can imagine. And on top of that was a girdle of precious stones, rubies, diamonds, everything. So I said, oh my God, with those cups you have to return it the next year. That's honor bound. So I got a special seat in the airplane. We took good care of it, took it back home, and everything was peaceful for a while until my son, who was 11 years old then, said, Dad, I lost it. I said, lost what? The big stone. You mean the ruby? Oh my God, I'm ruined. So I, of course, changed my underwear and do whatever you do. And I went next day to Bailey Banks and Biddle, which is the fancy jewelry store. And I said, oh, Mr. Chance, I'll have to look into this carefully. Come back tomorrow. Well, of course, I didn't sleep that night, but came back the next morning. He said, Mr. Chance, I have good news for you. You're in the wrong store. Go next door to the 5 and 10 cent store. They're all glass. So I got the trophy back to well, one of the great features of the end of the war was that the Guggenheim Foundation, which usually has strict admission application, came to me and said, you and the others who've given up your chosen profession, in my case, biochemistry, for the war 6 years, can have a 2-year fellowship to go wherever you want to go. And I said, that smells like Sweden, because that was Sweden and Switzerland were the only places you could go. And so I went to Hugo Terrell's Nobel Medical Institute, quite innocent. And Suna Bergstrom, who was my mentor, said, don't bring money, bring an expensive car. So we brought an expensive car, drove it to Stockholm, traded it for a boat, which was a good thing to do. And at that time, Terrell's laboratory was small and cramped. They hadn't built the research palaces at Solnahagen. And I was given the coat locker. It turned out to be rather long, but about so wide, and just right for one person. And of course that was heaven for me, because they were preparing very pure these enzymes which change their spectrum when they combine with the substrate. And we had a great time there, as it says, studying the many kinds of enzyme substrate compound, learning that iron, the enzyme, this axiom that the substrate modifies the enzyme. What we had learned about catalysis in physical chemistry, that the catalyst is immutable. It's not changed in the reaction. Well, all wrong. The substrate was changing the valence of the iron to valences that were very unusual, 5 and 6. And with Philip George, we adumbrated this theory. And so with these data in hand, I intrepidly went to Cambridge University. Well, in those days, if you had a competitor, you didn't greet him, you didn't collaborate with him, you exterminated him. And that's what they did. They wrote vituperative papers against each other, as if firing intellectual salvos at each other. Well, I crossed the no man's land to go to England, to the laboratory of David Kalin. And he was a little Polish guy, very smart, very kind in a way, although very, very stubborn. And when a wagon load of electronic equipment appeared in a laboratory, which the most modern instrument was called the Dubose colorimeter, which was just a color matching device. There was utter silence. Well, they gave me space, and I enjoyed working there. I got to know David Kalin, Hartree, and so forth, reestablish my coupling to the physiology laboratory, which was 100 meters apart. And haven't forgotten David Kalin as a man who was intensely proud, intensely skilled, and who resisted the idea that the work of Claude and Palladio and Didou showed that these intracellular organelles contained enzymes, lots of enzymes. In fact, all of Kalin's work was embodied with a organelle termed a mitochondrion. Well, that was a dirty word, and let's see. Let me see which way I'm going. Here we go. Sorry. Reverse. Yeah. This instilled in me the desire to improve upon the hand spectroscope and to develop a spectrophotometer that would work through tissues and organelles. And indeed, this was the problem of the time, because Claude and Didou and others, Palladio, had prepared these organelles, but they didn't know what they contained in the way of enzymes. And one of them was called the mitochondrion, which is one of the most prominent organelles of the cell, and as it turned out, is the powerhouse of the cell. Well, in order to look through this turbid suspension of mitochondria, we had to have a compensating wavelength to remove the scattering and an active wavelength to measure the signal. And indeed, the part that Kalin was able to see was the ABC part, not realizing that if he had, well, let's say an aphakic eye, he could have seen the ultraviolet, and there were not only these bands corresponding to the visible band, but they showed a homologous band, which mentioned NADH, 40 times bigger, and 40 times the molarity amount, and a trough here due to flavoprotein. And it turned out that these two components not only are there, but they are, I'll just come back to this, well, it doesn't show right away. They are fluorescent. They are biomarkers, fluorescent biomarkers, and they're used extensively, although they're termed autofluorescents. The molecular engineers don't understand where they came from, but that's all right. They make use of them. Dave Piston-Watt-Webb and many others taking advantage of the fact that this is a characteristic signal of mitochondria. Now, these are in the reduced state. When you stir in oxygen, then this band disappears and this one intensifies. So there is things going in the opposite directions. And when they do that, the engineer says, I'll take the ratio and be independent of the amount. So that's what we did, and proved to Kalin, well, I wouldn't say proved, got him to accept the fact that the mitochondrion contained his respiratory components. Furthermore, Otto Warburg, the famous biochemist, had isolated NADH from cells, but he didn't know that it belonged to the mitochondria. In fact, I don't think he wanted to admit that, because that would have brought his work together with that of Kalin, and that wasn't the style at that time. So now the phosphorylation of ADP to ATP, which Aaron mentioned last night, is very fast. We had to lower the temperature to 24 degrees and build a special flow apparatus to measure the rate of reaction. Because again, these were turbid. But we found at 24 degrees the half-time was 70 milliseconds, and calculated to room temperature was only 10 milliseconds. So in 10 milliseconds, this organelle can phosphorylate ADP to ATP. But at the same time, of interest to the physiologist, it can clean up calcium. So it is a calcium pump and an ATP generator. This, of course, has opened up a whole field of fluorescent signals from tissue, and as I say, is being pursued here in diabetes, in cancer, and in stem cell studies. We wondered whether we could get these signals from the human brain, and at Loma Linda Hospital, where they were connecting the external carotid to the internal carotid in order to supply more oxygen to the brain in people who had fainting spells, we observed through the window of the surgery that when the superficial temporal artery was open, that the flavoprotein signal was stronger than when it was not, showing that the operation was efficacious as far as oxygen transport, mitochondrial function. So this is the summary that I've mentioned already, that we had two biomarkers of mitochondrial function which serve us well in apoptosis, the signal changes, in drug therapy, the signal changes, and in stem cell differentiation, the signal changes. So this is a hot topic with the molecular geneticist who has failed to find a signal corresponding to cell differentiation in myocytes. We were still physicists, and together with Don DeBoll, who was famous for having worked in Arnold Beckman's garage and put together his first pH meter without merit, and we decided to see whether quantum mechanical tunneling could be demonstrated in a biological system. Well, of course, we took photobiology because you could turn it on with a flash. Secondly, we wanted to turn it on in a microsecond. Therefore, the ordinary flash lamps didn't work. So at that time, Neyman and Charlie Towns were making optical lasers. So we bought a ruby rod, flash lamps, and made our own laser, which gave us a microsecond flash and activated the sample. Well, if it were tunneling, we figured it would work just as well at low temperature as room temperature. So we put our sample in a Dewar flask in liquid nitrogen and with a spectrophotometer looked to see whether electron transport had occurred during the flash. Well, to our amazement and gratification, it had. Not only this jump is the oxidation of a cytochrome with a half-time of 3 microseconds at liquid nitrogen temperature. This was amazing because chemical reactions usually have a 10 kilocalorie energy of activation. This had a 0 energy of activation and could only be electron tunneling. So this has opened up a whole new field. This is our mechanism, which I won't belabor you with. A quantum mechanical yardstick. The tunneling distance is about 19 angstroms. Not only electron tunneling, but also proton tunneling, to the extent that we had a lovely symposium at the Royal Society last November on tunneling mechanisms in biology a great satisfaction. So that was another adventure that was fruitful. Well, George Rada and I were having a drink in Copenhagen and challenged each other to see whether magnetic resonance spectroscopy could be scaled up to the human leg. And Magnex said they could make a magnet, and we both ordered a magnet at the same time, and they both arrived at the same time. So then it was a question of who would get the first publication. Well, we had a volunteer leg. There was a standard article that would contract, break down ATP, increase phosphocreatine, decrease phosphocreatine, and increase inorganic phosphate. And this leg was available night and day. So we did get the first publication, which we put in the PNAS, and George came along with excellent results later. And one of his collaborators was the wife of the late and lamented Paul Lauterberg. There was a dichotomy in the field. We were biochemists, and we knew that MRI would take a long time to develop, and it had no biochemistry. It still doesn't have any biochemistry. So we were spectroscopists. And the good news is that now that they have 7 and 9 Tesla magnets costing millions of dollars, but they have them, that you can do spectroscopy with those magnets. So you will see in the next year or two that phosphorus, carbon, other isotopes, and also polarized isotopes will be doing good biochemistry imaged in MRI. So we're hopeful. We wondered whether we could get a signal from my head. Well, we did, but the model was mayonnaise. In other words, a lot of fat and water. So those were the first signals, spectroscopy signals from the head. Well, now let's make the transition to the topic of current interest, namely near-infrared spectroscopy for breast cancer detection, brain functional activity, and muscle bioenergetics. Those are the 3 things that it excels at. And we were aware of the spectrum of hemoglobin in the near-infrared region. Where is near-infrared? Well beyond the range of these fluorescent lights, which are green, very little red. The tungsten light does emit red light, and you will notice that if you hold your hand up to a tungsten light, you could see red through it. Well, that was known in the 1934s by Kramer and others, and we capitalized together with Qingming on using the fact that the deoxy, that's the purple color of hemoglobin, and the pink color, oxy, differed in spectral absorption in the near-infrared region. Why that region? I just told you that you can see light through your hand because the scattering and absorption of light in the red region is low enough so that even though you lose a lot of light, you get enough through to be useful. So indeed, all of you, I'm sure, know everything about electronics. Use the LED, 3-wavelength LED, voltage to current converter, a digital gain control, sample and hold, ADC board, and storage, and a computer display. In order to look at a tissue, you want to be able to look at a number of places simultaneously. So you put LED 3-wavelength in the middle, and then you have a circle of detectors. and then you just timeshare them as you would expect, and you can therefore have a multi-channel instrument. This has been useful in breast cancer detection. While this may seem ridiculous to you, you should know that the incidence of breast cancer is increasing rapidly in the Asian countries that and that it soon will be epidemic in proportions. The reason is probably that your diet is changing. You have more adipose because you go to McBurger too often, and so obesity is creeping up upon you. I hope not you, but watch out. And with that, there's tendency not only for diabetes but other diseases. So we place our probe right on the breast. It automatically scans through the 8 detectors and gives a display on your laptop of what's going on. Well, this we've studied for 7 years, because if you're doing a translational problem from the bench to the bedside, as they say, that's a 7-year itch, because it takes hundreds of studies to validate that it's really working. So we coupled to several hospitals, not only here. I don't want to wake you up. And acquired a data bank for this device, which measured the increase of hemoglobin in a cancer, because a cancer needs extra blood to grow. So it grows its own blood vessels, angiogenesis. It's also greedy and has mitochondria and uses up the oxygen. So it is angiogenic and deoxygenated. And using those 2 criteria, we made a 2-dimensional nomogram shown here, in which we plotted on the abscissa the angiogenesis, the increased blood volume, and on the ordinate, the deoxygenation. And we're able to find data on 44 cancers that were in this region, and I think 80 or more normals, which were in this region. So they segregate, which is a good thing. And so we draw a line between the two. And the cancers were 95% certain to be in this region, and the non-cancers were to be in this region. You'll notice here that 2 cancers got into the normal region, but that was 7 years ago, and the 2 ladies are going strong. So I don't know who's right and who's wrong. They're happy. Also, these balloons answer the question. The radiologist always says, how big a cancer can you measure, or how little can you measure? And this little one here, right here, they're 1 centimeter, 2 centimeters, 3, 4, 5. So we had no trouble with small and deep cancers. So Dr. Nyoka is continuing this study at the NUS, National University Hospital, Singapore, the National Cancer Hospital there. And we have good feelings that there will be tech transfer to Singapore, and we hope that this may also can occur here. On this card. So this gave us a 94% accuracy over 7 years, which is rather good. it's difficult to get comparable data. I know that mammography has trouble with the young, dense breasts, which we don't have. We know that NMR has difficulty with calcifications. And we know that ultrasound doesn't find out whether it's cancer or not. PET is good, positron emission tomography is good, expensive and takes a while. So those are what we call intrinsic biomarkers. They're already there. You don't have to inject. On the other hand, the whole field of molecular imaging is based upon injection of biomarkers, which are very clever. They may do all sorts of stunts in recognizing the cancer, but they're not FDA approved, except for one, and that was approved some time ago for studies of the eye and of the liver. It's called a tricarbocyanine cardiogreen, and Dr. Nioka has actually studied in China several cases where this is a normal one with a very small signal at the top and these are cancers. And the interesting thing is that the time course of release of the dye from the cancer is delayed in the case of the cancers and short in the case of the non-cancer. So it has what you call specificity and will be followed up. So we have the intrinsic biomarkers of hemoglobin, oxy and deoxy, and then we have one and only one injectable biomarker. So we hope that that situation will change, especially here in China. Well, this is a field day for microelectronics because all the circuit elements that I've shown you can be made in surface mount or CMOS, just like your cell phone. They can be telemetred out if you want. So we have been engaged in discussing with Qingming and discussing with Syntec and others in Singapore, and guess where the best place right now is? Bombay. So we have put this together in a handheld, pocket-sized device. This is our breadboard device. It's just about the same size as a glucosometer. It has two light sources, a detector, and it rings a bell when it discovers an anomaly. Well, now, I don't know how many of you know about litigation. The patient who receives an incorrect diagnosis in USA will immediately be snatched up by a lawyer and sue the device for $1 million for a false diagnosis. So we don't try to diagnose. We try to early warn, to tell the subject that they have to go to a doctor. Now, all these data from the handheld scanner are recorded on a digital chip, so she can doesn't have to tell the clinician what she found. And we think that this may be a way to reach underserved population who don't have access to mammography, ultrasound, MRI. And this is a way that biomedical optics can reach out to the less fortunate population and get them to detect their cancer early. Why early? Because in early, it's operable. You can remove the cancer and it won't spread through your body. If it's 2 or 3 centimeters in size, the likelihood that it's in your bones, all through your body, is very high. And then you go into chemotherapy, you lose your hair, you lose your mind. So this is one way in which we hope that biomedical engineering can outreach to the underserved population. So that's what it says here, and to particularly surface mount or CMOS chip, which certainly is possible here, it's possible in Hong Kong, it's possible in Taiwan, it's possible in Singapore. So that's where we want to go. Now my last topic I call the golden fleece because it's completely elusive, and it's for brain function. We've already visited Ching-Ming's laboratory and see that he's hot on the trail. It's out there somewhere. Remember Ulysses. So not only we're interested in measuring the function of the brain in solving problems, but also extending this to interpersonal interactions. Because remember, the forebrain is the site in which you have a conscience. If you get shot in the forebrain, you won't kiss your wife goodbye, you won't flush the toilet, you won't pay your bills. So, furthermore, your creative thinking occurs in the forebrain. So we have great faith in the fact that NIR monitoring of blood volume changes in the forebrain will provide, as it says, a faster, cheaper, portable brain imaging. We project light through the skin, the skull, the arachnoid space, the pia mater, into the brain cortex, which is a thin line of cells about 1.5 to 2 centimeters deep. And we can project light from the sources that reaches the detector. Do we lose a lot? Sure we lose a lot, but we start with 10 to the 16 photons per second, and we end with 10 to the 8. Well, that's fair, as the Australians say, fair dinkum. And so we don't have any trouble with signal to noise, and we have multiple sources and multiple detectors. In fact, 16 detectors, just as Ching-Ming had. And we measure the increment of blood flow and the increment of oxygenation, and the particular pixels which are activated show in red color. And you'll see that the blood flow and the oxygenation are not exactly congruent. That's because metabolism activity is localized, because that's where you're thinking, and that doesn't always muster the increment of blood flow. What we're mainly interested in is your conscience, whether you have a guilty conscience on telling a lie. Remember, no, I shouldn't say remember, but in case you do, to realize that you have no decision making to tell the truth. The truth comes out automatically. You have to make a decision not to tell the truth and to tell a lie. Well, of course, this is interesting to all sorts of government agencies, and we're pursuing it with the above-mentioned people. So, in addition to that, we have the ability to know whether you've learned something. I hope you've learned something. And when the brain has learned something, well, when the brain hasn't learned anything, it's scattered all over the forebrain. That is, you don't know where to solve the problem. Well, if you have solved the problem, you localize the response. So we are engaged in a program with the third graders of Singapore, who in the third grade have to make the transition from a pictogram to numerical solution. And that's where they lose most of the young students, because they're unable to do this. And that project is ongoing there. And I think it's a good one for the schools here to learn the difficulty in problem solution. Now here we are on the right, you tell the truth, there's no mental activation. On the left, I said, who, me? I didn't do it. And so that activates in a particular place. Well, not just the same place in all people. It's a different place in different people. So you have to be calibrated for your lying spot. But nevertheless, that has emboldened us to make an airport surveillance device where we have the people seated waiting to board an airplane, just about, not too well. And we have in a concealed ceiling a NIR source, a parabolic mirror, and also a TV monitor so we can monitor which subject should be examined. Well, to stimulate them, of course, on the left, we have an alerting display, which presumably is the Twin Towers of New York City crashing to the ground, or some other stimulus. And this, of course, is of interest to the military mind. But my interest is in minimally fettered brain function, school children. Remote sensing. There, I'd like to go to a board meeting. Maybe not our board meeting, but a board meeting where they're about to oust the chairman and find out who's telling the truth and who's telling a lie. And also their business dealings, where you'd hope that I could see what's going on in your brain and say, goodbye, or I'll sign it right here. Furthermore, we want to be able to communicate with computers, because that will be a great saving of time if we can operate the keyboard electronically from our brain. And of course, there's always the marriage ceremony where trust is involved. Should I really trust him? So these are the kinds of answers that we hope to get in the next generation of devices. The potentiality is there, and so that's what we say. Can brain-computer and brain-brain coupling be established? So thank you very much.
Thank you, Bert. It's really amazing. From this talk, what was our you can find British stories, a pioneering new technique. It's, you can find the use the earliest computer in university as solve nonlinear functions for the biochemistry. They use first one to use the MRI. First one, the one the pioneer who used the lasers, even near infrared. So you can say always use this kind of new technique. So, any question? Oh. Okay. Lady first. Okay.
Okay, thank you very much. And I have noticed that there's a photo of you in the BC Center's booklist. There's this picture. And I noticed that in this picture you stand in front of a blackboard. And in this photo I noticed, I guess, and that there's a feedback circuit, right? Feedback circuit drawn in the blackboard. I think that feedback is a classic conception in automation, right? Feedback, this conception of feedback, yeah, is the classic conception in automation. And I want to ask you did you ever use the technology of automation in biomedicine or other fields you have researched in?
Well, I've lived with feedback since age 13, because in ship steering you have to have feedback, negative feedback, otherwise the system will oscillate. But then, of course, the theories of Nyquist and others were quite familiar to us, and we had feedback in many of the systems of the radar laboratory. So, and of course, the most important feedback was having fired a shot that the plane fell down. I could tell you a tale. Norbert Wiener, who was the famous mathematician, was working for us, and he made a computer simulation of how his anti-aircraft device would work. Well, we tried it out. We noticed after one shot that the tracking dish always went down to follow the burning up plane. So Norbert would never admit failure. So his program anticipated that the shot would be perfect. We never used it.
Next.
First of all, thank you very much for giving us a wonderful speech. We are amazed that you have got a fabulous achievements in many fields, including science, philosophy, and even the Olympic Games champion. It seems that everything is easy for you. So I just want to ask, what's the most difficult thing in your life, and how did you overcome it? Could you share a concrete experience with us? Thank you.
Well, I think that my PhD thesis was most difficult. Because I was absolutely alone at Cambridge. Canterbriggans don't work during the summer, and that was the only time I had. So I drilled my holes, I glued my glue, I soldered my circuits, and that was great because I knew whether if something went bad, I knew what it was. It was me. So that was.
Okay. Okay.
There are many engineering research students confusing about their further research after they have a completion of new instrument. Would you please give some suggestions for them?
Could you repeat it? I want to get the question exactly. No. Ching Meng, what was the question?
There are many engineering research students confusing about their future research after they have finished to do a new instrument. So would you give me some suggestions for them to do the future research?
I guess his question, our question is since many students who's major in engineering, they just want to know, hope you can give some suggestion for their how to develop some new instruments or do something new technique.
Well, each one of my PhD students has the task of making his own instrument. Now, this is very much against the trend, certainly in Singapore, where the goal is to buy the most expensive instrument. And of course, they don't know what its limitations are. And I deplore this. I think the student should really know what he's doing, just like he should know in biochemistry, each step. So, thank you for the question.
Britton Chance, first thanks for your wonderful speech. I'm very interested in the application of stem cells in the brain disease treatment. All you haven't talked about this topic, but I think you can give some ideas to us. The implantation of stem cells in the in the boy disease treatment is still controversial. But do you think it is the most effective treatment methods since there are not effective methods in neural disease treatment? If it is, then what's the optimal cell source and how to solve the chronic repellence and the security? Thank you.
I guess this question is about the stem cell. Stem cell. If you want to, what's your comment about the stem cell to do the therapy in your some kind of disease? Use stem cell. Stem cell, yeah.
Which
The question is, 你是问他就是说用。She wants to know the application to use the stem cell for the therapy in some kind of brain disease, neural disease.
Well, we are studying brain cancers, gliomas. We're studying dementias. Brain diseases, of course, we want to be able to study without opening the skull. And so we're very much interested in stroke, brain hemorrhage, and brain cancer, gliomas, and also we want to study dementias due to Alzheimer's because all of those are involved in a series of studies. Once you get into clinical studies, you realize that you have to do enough of them to get a statistical significant result. But they're possible. If you're interested, go do it.
Okay. Okay. One last question.
This lady over here. This other man down there. We'll get you there.
First, thank you for your wonderful speech. I'm a PhD student. I have met a little bit trouble in my research, so I want to get your help. We have purified a novel bioactive peptide which named glycine, and it can increase the blood glucose by subcutaneous injection. But when intravenous injection, the peptide will decrease the blood glucose. We know why we get different results by different methods to administration of the peptide. My question is, if we can use your novel method to help us to find the different targets and what should we do next?
I have to ask whether this is to control blood flow or whether it is to, you mentioned glucose, but it's really a blood flow regulator. Well, reduced body blood flow, particularly in exercise, diabetes, type 2 diabetes, have decreased blood flow to their legs, and often they will lose their feet. So we monitor the recovery from exercise as a standard procedure, and that should help you. There is a group in Singapore who are making very widespread study of cohorts, and for which this is an ideal technique. There's a clinic at the University of Pennsylvania where this technique is going on. So it is available. Be happy. And then this lady over here, you've been trying to get back.
All right.
You were the first stop.
Good evening, Britton Chance. I want to know, you have done so many work in many fields. Which exercise is the most proud or memorable for you?
Which is the one that comes back.
Which is the piece of work you're most proud of?
You have done so many works. Which exercise is the most proud or memorable for you?
Well, that's a tough question. We're proud of the Olympics. In sports, you know whether you finish first. There's no doubt about it. You cross the finish line. In science, it may be 20 years before what you do is really understood fully. If it's a good discovery, it'll take a long while. There's an inverse relationship. So they're both fun.
Okay, let's give this last question to the high school student. Okay.
As we know, you have been to China for many times. What do you think about China? And the next question is, as a high school student, can you give us some suggestion in the researching road and for the freshman or even postgraduate students? Some suggestions in researching or and studying science.
So, what is the question? What can I tell you?
Can you give us some suggestion in studying and researching science for high school students, freshmen, and postgraduate students?
Well, thank you for the question. We're very interested in high school students. Every summer, we invite 10 from the high schools in the Philadelphia area. They work with us for 3 weeks. They study their brains. They write a report. They put up a poster in the annual science fair. They get admitted to the Ivy League colleges. And so it's a wonderful experience for us and for them. So we're very proud of our interaction with the high school. Now, of course, here we're much more selective in admission to the high schools. I think the program would do very well here. But don't forget the third graders.
Okay. Thanks to the third chance. Thank you very much.
Oh my God.